shot over here, it is just considered one die. Okay? So once you finish all the front-end process, then transfer to the packaging company. For example, like ASE or OSE, we need to put into the like a cutter and then do the dicing to separate all the dies. So initially it's on the wafer, and then it becomes like maybe 100 dies, and then from each die they do the packaging. And the one that I just mentioned, for example, the CD target or the overlay target, usually it is a space between all the dies. So once you cut it, of course, it's a sacrifice, disappear. But when they do the metrology, they will do it over here so that they will minimize the impact to the die itself. Okay. So before we go that, we need to, for the metrology, we need to tell the difference between accuracy and precision. Okay, so in ideal case, everything will be on the top right corner. In ideal case, we want it to be like this, right? We want it to be like this. So this is like a high accuracy and high precision. Okay, but there's two things that is different. One is that if this is I'd like to kind of compare this to archery. When you do the archery, you have a target, and you use like a bow and arrow, and then try to shoot at the center. If it is you are a very good archery athlete, right? You put everything almost at the center, everything on the goal. However, if your bow has some issue, and you are even though you are a good athlete, you have a very good consistency, but everything got missing. For here, it is on left side. So you still have very good precision. The precision is very high, but the accuracy is low because you miss the target. You miss the target, so everything is the precision-wise, here and here is about the same, but accuracy-wise is very different. So what does that mean? It means that you take the mean value of your shooting, or basically your shooting. You take the average, and if the 3 sigma is just as small as this one, then you tell you this is a good precision. But if the mean value is different from your target, then the accuracy is low. On the other hand, over here, the mean value, overall the average, you're still on target. But compared to here, you have like 10 arrows on the center. Here, you only have 2 on the center, in the center. Like the other 8 are outside the center. You have a big distribution. Your 3 sigma is much higher, so your precision is low, even though your average is the same. Okay, so for archery athlete, okay, here you pretty much have to adjust your aiming mechanism so that you are, for example, if you are aiming here, maybe another time you need to aim here, so you will move your distribution to the center. And for this one, you pretty much have to increase your stability so that you will minimize this one to here. So precision and accuracy is two different metrics. Yeah. Same thing for the tool or process, right? If you have just take a CD as an example. If you have the CD very narrow distribution and just on left side, then maybe you just adjust like the dose or adjust the focus location. Then you can move everything there. However, if you have a big distribution, usually that means you need to upgrade your tool so that it has a better process control, and then it's a much bigger engineering task to be able to narrow the distribution. Okay. So CD metrology. Okay. Here, two examples. One is a line and one is a hole. CD measurement. Usually, we use it for like a SEM, the scanning electron microscope. And recently, because they wanted to have a more data sample, so they start to use the optical CD. And CD, same, they use an electron beam and to the sample, and then and energy usually is a lower energy E-beam. And E-beam, if you have a high energy E-beam, it can damage the photoresist, and then or you would charge up the sample. I mean, the charge up the photoresist, so your measurement will not be as accurate. And the CD SEM, the repeatability usually is 3 sigma, as I mentioned here. The 3 sigma here is usually need to be 1% of what you measure. So for example, if you're measuring the 100 nanometer features, the 3 sigma need to be like 1 nanometer or lower. And it say that if we need to measure like 100 nanometer, 100 patterns or 1,000 patterns on one wafers, it need to be automatic, because otherwise your throughput is too low. So automation is important, and therefore you need like a pattern recognition so that they will move the measurement from one shot to another shot. And APC is a very common use in the fab. It stands for automatic process correction. So that means, as I mentioned, if your CD is say too big and it is line, then you tell you the system you need to adjust the exposure dose so that the CD will become smaller. Yeah. So it's a feedback to the system to tell you so that the target is reached. And CD variation metrology usually should be we need to measure the CD variation across a die. We say that like a intra, there's a several area that need to be measured. The CD variation has several areas. So when we measure the CD variation, at least there's 3 things that we need to do. Okay. One is called intra-die. So each die inside here, we measure like many like a different area for within that die. Okay. But if this is measured, usually this is for R&D. Okay. For production, as I mentioned, usually there's some like a test key over here. Is for manufacturing. Usually we don't do that during the manufacturing. We don't touch the die itself. But when you do the R&D, you need to measure what's the CD variation. You need to measure maybe 10 to 100 points per die. And then within the wafer, you probably measure somewhere in the center, at least like a center of the wafer and edge of the wafer, and somewhere in between. So maybe 5 to 20 dies taken for one wafer. So we call it like a inter-die or intra-wafer. Yeah. Within wafers, you need to measure within wafer CD variation. And then on one cassette, right? You have many wafers. Maybe this is slot 1, then this is slot 25, and this is slot 12. Maybe you pick like 2 wafers and then to measure the CD, so that you cover basically everything. Within die, you want to know what's a CD. Just within the die, right? What's a CD variation within one die? And what's a CD variation within one wafer? And what's the CD variation from wafer to wafer? And then for HVM, you want to measure from today to yesterday. What's a CD change? Okay. So you can see like a CD, just CD variation, pretty much you will have like a 3 to 4 that you need to measure. So CD variations usually will show it for CDU. And if this is not complicated enough, inter-wafer, we will have enter output. Remember, because within, when you have like putting wafer from one lot, you need to go to the track, right? You will do the soft bake, and then you do the scanner, and then come back to the PEB, post-exposure bake, and then develop. Okay, for the track engineer, if you want to do the experiment, you want to fix the same hot plate. Hot plate, say that you use like a hot plate number 3 for your experiment. So you use that for hot plate 3 for soft bake, hot plate number 8 for your PEB, and then you do your exposure. So every time you do 3 and 8 for your experiment, and then your manager will ask you, you need to do like say one lot, everything fix the PEB at number 8, but you split it to number 1, number 2, number 3. Yeah. All the wafer, you change different hot plate for the soft bake. Everything the same except the hot plate. Soft bake with a different hot plate. Same temperature though. You say that the soft bake is 110 C and 60 seconds. But trust me, this one it might be 110.1, this one may 109.9, this one may be 109.85. Right? Each hot plate may have a very small within spec temperature difference, and that will result in CD variation. So as an engineer, you might be required to do the split to make sure the CD variation from the hot plate is very small. And the same thing, you might be asked to do the split for PEB. Different hot plate. And then there's a scanner on your this process. You have a scanner number 1, number 2, number 3. Then you go to different scanners, right? So that's why for HVM, high volume manufacturing, they need to take a lot of data for the CD variation within die, within wafer, and then between tools. With the same tool, maybe like a different wafer. And I think most importantly, especially when you about to transfer the litho process to from RD to the fab, they will usually want the data. How's the hot plate? How's the scanner? How stable is the process? So metrology, especially CD metrology, yeah, it is somewhat complicated. And it is something that you'll encounter at your job. And that is not just for like advanced manufacturing. I mean, even for low end, like I-9 or 248, like not just in TSMC, I'm sure in the SE or OSE, they probably need to do this also. They need to do the cross machine and make sure the CD is very stable. It's not vary from machine to machine. And even with the same machine, you have like a different component, right? Different hot plate. You want to make sure all the hot plate have the same behavior. Because otherwise, you will start to see something have the low yield, and then they start to trace. Actually, it's like one hot plate is 1 degree different than others. Everything is 110 degree, and that hot plate is 108, for example. And then that causes a low yield. The yield from say 90% to like 60%. And it is all from that hot plate that has a lower temperature. Okay? Okay, so how does a CD-SEM image look like? Okay? CD-SEM image look like this, right? So you can see it look like this. And then so how does that mean? Is that usually you have border over here that is especially very bright. And here actually, here and here. This is brighter, but not as bright as this, right? So actually, here is the slope of the photoresist, for example. Okay, so when we try to measure the CD, right? Just exaggerate it from here to here. Are we measuring here? Are we measuring here? Are we measuring here? Or measuring here? Okay. So some metrology engineer try to decide it. Do we do like a 10% from the bottom or 10% from the top? Right? So that would decide it. Are you measuring over here to here? Or we measure over here to here? How do we measure that? So metrology engineer need to tell you that. Or as a metrology engineer, you need to make the decision. What do you do 10% or you do 20%? Or do you do 50%? Because the CD will be all different. And defect, wafer defect inspection. Okay, so this is a wafer, right? And if you have defect here, so this is usually for this two-way. One is a light beam, one is an E-beam. E-beam is more accurate, but very slow. Light beam is faster, but resolution is lower. So you have the light beam going through here and here, back and forth. And if you see the defect, because you usually have a database, that it should look like this. So if these two subtract each other, then the defect will show up. So they usually take the difference of the image, 1 minus 2, and to tell you if there's a defect over here or not, and tell you the location. So then you need to make a decision. Do you want to continue the process, or if this is lethal, then you can wash your photoresist and redo the process. We call it rework. So this is a wafer inspection. And usually the tool look like these. Also, yeah, the laser beam coming here, and then there's a detector. So that's how they keep rotating the wafer, and to be able to find out what the wafer image look like. And that's just some example of the image, defect image. Yeah, some of them, yeah, the wafer, like a pattern disappear, or some irregular area become, and some areas that we call it scumming. Yeah, like a photoresist become shorter or broken, but basically there's some like a particle over here to show that. Okay, so this inspection is like a optical from KLA Tengku, and then they tell you that, oh, this the scanner is what, the track is what, the process is what, using bark, photoresist, and then top coat. Yeah. After you finish that, then they do the wafer inspection, and as they say that they found 3 defects, and then divided by the area, so the defect density is this. Yeah. Okay. So next one is overlay. So overlay. Yeah, so we have photo mask, and then they, on the wafer, we have alignment mark, and then from previous level, and then we need to do the new one and see how well they compare to the previous. So that's why we usually need to do optical, because optical can penetrate to the next level, the previous level. So usually image look like this. Okay, there's a two way. We call this a box in box, and this called bar in bar. Okay, so as you can see, this is a previous layer. This is the current layer, and then they catch both of these. So this is X, so they can find the center. So this is X, they can find the center. So they want to compare the X from a previous layer and X in the current layer, how much different it is, and sample Y. This is a 2 box, right? They need to find the center. This is for current, they need to find the center. And same thing for the box in box. So box in box, you can see that for this one, they just catch. This is the previous layer. This is the current layer. Current layer, they catch the inner and decided this is a center. And previous layer, they catch the outer. They find the center. I mean, catch inner or outer doesn't matter, but what matters most is that can they focus on both layers, have a very clear image or not, and so that they can find the distance between the X and distance between the Y, and that's the overlay they measure and then also decided if this delta is within spec or not. If not, then maybe usually they need to rework, wash the photoresist, and then do the patterning again. And they need to dial in the delta. If this is out of spec, for example, just assume the spec is, just assume this is spec is assume spec is 20 nanometer, and then you measure this one. The delta here is 15. The delta here is say put 40. So Y overlay is okay, it's within the spec, but X is out of spec. So usually you need to dial in like the overlay. So when you put in the wafer, there's a place that you can dial in overlay correction. And then you need to try to make the 40 to be lower than 20. By dial in the number overlay correction, say that you put in negative 30. So that you'll be lower than 20. So that's how overlay correction, how they measure that and how they do the correction. And then of course, once you do the process again, then you need to measure if this correct or not. If not, maybe you need to dial in more. Say that, so you put in, initially it's 40, you put in negative 30, and then after that, you find out that it is 21, right? So the correction doesn't do enough. So then you need to put in 40. And then maybe, hopefully maybe it's become 10. Right? However, if you put in 30, then it becomes negative 25. Then means that it's very sensitive. So then you need to dial in, maybe dial in 15. So that hopefully will become 0 next time. So a lot of time you just need to do some experiment to find out how much it is. Okay, so that's how it happens at the fab. Yeah, usually a lot of time you can overcorrect. So we try to be conservative when we do the correction. And there's several things that will contribute to overlay. Okay? Give two examples. The majority is these two types. One we call it translational error, and one is rotational error. Okay? Translational means your target is here, but you shift to one direction. For here, it's both x and y. Right? This is translational. And one is rotational. You want it to be like here. Then you rotate 30 degrees. This is rotational. So on the whole wafer measurement, you will look like this. You will see like you see a lot of arrows. So basically, it tells you this is starting from, this is previous layer, this is current layer. So the bigger the arrows means the bigger overlay arrow, right? So the small, so say here, this is small and this is big. But from here you see like all shift from same direction, right? Shift from same direction. So we say this is translation, right? And here is rotational, means that in the center, the arrow is very small, but at the edge is much bigger, and it is the same direction. It's clockwise. So this is rotational, and this is a translational overlay arrow. Yeah. And for rotational, a lot of time is related to this. Yeah. This is the arrow is related to the wafer radius and from the mask and to the wafer. And delta T is temperature. The alpha is thermal coefficient. So the thermal coefficient, the bigger, then you'll find out you become like a rotational overlay arrows. Yeah. And so this is talking about like the design. Okay. So from the design, if you everything put into the just perfect. Okay, so that's the top image over here. Ideally, you put everything here. This is a cross section, of course. The oxide is here, and then the implant is here. Then the P-type silicon is here. So once you have the oxide have some overlay arrow, then this area is open, right? So whenever you do the implant, then there's some issue here. Yeah. So you're not covered by the N+ over here anymore. Okay. So the solution is that you should always leave some margin here, so that even though oxide and this implant layer is not perfect, when you have some shift, when you have this delta shift, it will not cause the short problem. Over here also, if you everything just put it ideal, and then you have some overlay error in the y direction, then you will cause some implant short issue. You should always leave some margin, go some protrusion, so that even though it go back a little bit, then it will not cause the short issue. Okay. Here is kind of change the gear that yeah, maybe we'll talk about that next time. Yeah. So this is just the tool itself. Why we do like a dual stage, okay? Dual stage. Yeah, last but not least, we a lot of time we do experiment, but sometimes we need to do some simulation, because the simulation can do some prediction, and like we show in the very beginning, right? If we can use a simulation to tell you the pitch is not good, right? To tell you this illumination is better to replace by another because it has a better image contrast, then the simulation is 100 times or more faster, and will save you a lot of money and time. Okay, so we may or may not have time to talk about lithography simulation, but yeah, a lot of time, if you at your job has some simulation, it's better that you do the simulation before you implement that into like the real tool using real resist, because it will save you time and money. Okay, so I think we'll stop here, and then I will recap that with Mandarin Chinese in next hour. Okay, let's take a 10 minutes break.